Okay, we're ready to restart. Do you hear me? Thank you. So we have seen that the nature of the Bellman-Ford algorithm when it's distributed is that if the network is partitioned, it will count to infinity, and this can be avoided by having a safeguard which puts an upper bound on the network diameter, which is done by RIP. But it can be improved. Instead of with RIP, in most cases, we will not wait until we count to the value of 16. Instead, there are optimizations, and all distance vector routing protocols are concerned with avoiding this problem of slow convergence whenever the values are either the true values are infinite or there is values that don't make sense with respect to the current network topology. Two heuristics that are, for example, present in RIP is called route poisoning and split horizon. Split horizon is just common sense. If A routes a packet to some destination via B, then A should not announce this to B, because A gets from the logic of distance vector, the best thing that A had so far was from B. So there's no point repeating that from B. And in fact, in the example we saw before, the count to infinity was coming from the fact that A was repeating obsolete information to B that it had obtained from B before the failure. So that's avoiding that entirely is called split horizon. But a more radical improvement is whenever you detect that a route is not reachable, you immediately inform all your neighbors that this route is unreachable, which is equivalent to sending an update which is plus infinity. So that's called poisoning, in the sense we don't wait until the updates to be the calculations to percolate through the normal computation. We immediately inform all neighbors of this new value here. And furthermore, when a distance is received for a given destination, we freeze the destination for some time in order to avoid those oscillations that could occur in the count to infinity. So here we would force everybody to believe the destination is unreachable, which will at least avoid some routing loops. Here's an example. So let's redo the previous scenario where those two links are broken and D detects the failure of the link to E, for example. Then D immediately will send an update to all neighbors, in that case it's A, that the values of C and E are now non-reachable, that those distances, those values are not reachable. Right. So it will do that immediately, will not wait until the next update interval comes. And second, the routes that were learned from A, like little a and B, this and that prefix that had next hop A, D will not give that information to A. So this distance vector will contain only those things here, the local prefix D, and the other ones which are infinite here. So if we apply this new rule here, what will be the new status at A? What will A do after receiving this update here? I close the poll in a few seconds. And the majority says D, which means that both distances are infinite, which is not the correct answer. Once again, let's see why. Well, D A applies the distributed Bellman-Ford algorithm, the version that works. And remember, you need to see whether the update you receive is from the next hop. So A receives from D information that C and E are at an infinite distance. This was not the next hop, therefore there is no change. A had another path that went through interface L1 that has a distance of 3, so it will keep it, so no change. So it will not, A will not know that C and E are unreachable in this state. C is unreachable. However, for E, because the next hop was D, A adopts it immediately and declares that the distance is infinite. So in one iteration, E becomes unreachable also for A, but not yet C. So we will need one more iteration. In fact, well, because A was routing to C via its interface L1. So first, if L1 is still working, D doesn't know about this. So we should stay with this information if L1 would be working. But if L1 doesn't work, A will sooner or later detect the failure and will declare B and C as unreachable. And that will cause similar things here. So in just 2 messages that follow the detection of the failure locally by nodes A and D, the routing tables converge to the correct value. So we have removed, we have avoided the counts to infinity. So the combination of route poisoning and split horizon avoids entirely the count to infinity in this case. Now you can have more complicated scenarios where the loops don't involve just 2 nodes, but a larger number of nodes where there will be some count and will not be as nice, but still it will generally be very fast here. Of course, after some time, if that's the final state of affair, A and D do not have any path to B and C, so sooner and E, so sooner or later they will, by timeout, they will simply remove them from the routing table so that they don't use unnecessary space in the routing table. So this is what RIP does. It implements all the theory that I've explained, with the count to infinity being limited by taking infinity equals 16. It works over UDP, uses multicast addresses. Multicast because you can have shared, you can have multiple neighbors in an Ethernet LAN, for example, with multiple routers connected, like we saw for OSPF. By default, it's a slow protocol that sends an update every 30 seconds. And it uses authentication by simply shared password, shared secret on all the nodes in a given network. Apart from the secret that you need to type into all the nodes, then no configuration is required if you're happy with all costs being equal to 1. So you have a plug-and-play routing protocol, which is the main value of RIP. Distance vector is used in other protocols, for example, in the context of mobile networks, ad hoc networks, you have AODV. In the context of data centers, you have Babel. And in enterprise networks, a competitor to OSPF, which is less popular now, but still is still used quite a lot, is EIGRP, which uses also Bellman-Ford, but does not, like RIP, does use, unlike RIP, some additional information. So the routing information base is not just the routing table, but it keeps a routing information base, which is more than the routing table, but still much less than OSPF here. And it uses a number of tricks to avoid the count to infinity that I will not go through. There are 2 of our old friends, the spanning tree protocol and OSPF, that also have to do with distance vector. If you think about it, what the spanning tree protocol does is that all bridges elect the route, and then they compute shortest paths to the route. And if you look at the details of what they do, is that the election is similar to Bellman-Ford, except instead of computing the shortest path, you compute the who has the best identifier, which is the smallest bridge identifier. And once you've computed that, you compute also the distance. The computation of distance is exactly Bellman-Ford. The computation, the election of the bridge, is a variant of Bellman-Ford where we replace addition by the minimum. We don't consider a distance to a root, but to a node, but we consider all potential nodes and find the minimum of their labels. And whoever has the minimum is adopted at the best, which can be shown to be a variant of Bellman-Ford. With a big difference, though. When we compute distances to a given node, then we have all the beauty of Bellman-Ford. In particular, if anything changes, we don't need to reset the network. We continue computing the distances, and we will converge to the new correct values here. So the spanning tree protocol has this property. If a link breaks, for example, that does not affect the connectivity of the network, if the network has redundancy and loses a link, and if this link, so if just a link breaks, then all nodes will compute a new distance to the root asynchronously and smoothly. However, when we elect the root bridge, this does not have the property that if the bridge dies, for example, then you cannot simply asynchronously continue computing as if nothing had happened before. You need to reset the system to inform everybody that they should do a new election of a new bridge here. This is why in the spanning tree protocol, there is a network-wide keep alive mechanism, which fortunately is easy because we have a tree. So the root sends a ping packet or a hello packet every few seconds along the spanning tree. And all bridges must monitor that they do receive this. If they don't receive it, they restart everything, including a new election procedure. So the election doesn't have the nice property of Bellman-Ford that you can do it asynchronously. Here you do need a reset. Our old friend OSPF is link state. That's the prototype of link state, but it's link state only in one area. What we have seen is that between areas, if we have more than one area, we have one area that should be in area 0, and the border routers that belong to both area 0 and another area will inject into their areas their distance vectors. I presented it a few weeks ago by saying they do as if they were directly connected with some distance, but in fact what they do in the terminology of distance vector is they inject into the topology database and through link state update to all routers in their area their own distance vectors here. So it uses the principle of distance vector, and we saw also that the formula that is used to compute the distance to a final destination that is not in the same area involves in fact the same update that we have in Bellman-Ford. So it is using Bellman-Ford. If we view the areas as nodes, so if we do a graph where the nodes are simply the areas, then in this graph, OSPF is in fact a hybrid of link state and distance vector. But here in OSPF, the count to infinity does not exist because the graph of the areas is an extremely simple graph. In fact, there must be always area 0 at the center. In OSPF, areas must be connected to area 0 and must not be connected to other areas. So area 1 cannot have a direct link to area 2. If there is such a direct link, OSPF will disable it, and the connection from area 1 to area 2 must go via area 0. So we have no area loop. We have just a star topology, and on such a topology, none of the difficult things of distance vector occur. This is why OSPF, even with this distance vector addition, continues to be a routing protocol with very fast convergence after changes here. Voila, we've done the main part. I will continue here with a bonus part on a question that is often asked, but we do shortest path routing. Is that a good idea to do? So let me start with a small question here. Does a routing protocol maximize the network utility in the sense of the utility we've seen in the course on congestion control, for example? I close the poll in a few seconds. The majority says no, which is the correct answer, because it minimizes the length of the path relative to the costs that are placed here. But in general, of course, this will not be optimal. For example, assume here I have a huge amount of traffic that goes according to the red arrow. So there is a small amount of traffic everywhere, but most traffic goes along the red arrows. And the bottleneck of this network is the link between B and E, which is here. So if that is the case, then it would be better if we take, for example, the utility function of proportional fairness. It would be better to deviate some traffic along the longer paths, because there we have more capacity here. So the TCP connections will get a better rate if 1/3 of the path of the flows goes the long way, another third the other medium way, and only 1/3 goes the short way. If we would do this, then we would probably, this is probably something like this we would have if we would like to maximize the sum of the rates of the TCP connections. But this is not done in the internet. What we do is truly we minimize the cost to destination, which will not be optimal if the traffic is very unbalanced. So one attempt to do this that you find in many routing protocols, enterprise routing protocols, for example, in ERG-IP of Cisco, is to use a cost that is dynamic and reflects, for example, the load or the delay here, which is a good idea. I mean, if a link is congested, if we take in the previous example here, if we do things in the way I presented, then this link will be congested. So the output buffer of router B will have a large queue and the delay will be very large here, or the utilization of the link will be very large here. So it would be a good idea to give a larger cost when this starts occurring to this link here. And this will attract the traffic to go to other links here. So a lot of traffic will go this way until they also become a bit congested, in which case their cost would increase. And similarly here, some traffic will originally not go here because of the cost of phi, which is very large. But when these costs here and there increase, then traffic will be eventually attracted here. So that's the idea that's behind that. In practice, this is done, for example, with formulas like this, where we can measure the delay on the link. But the delay is not always a good idea, because if we have ECN, then it's the load that matters more. So we could have something, a formula of this kind here, that is a simulation of the queuing formula that says that the delay becomes infinite when the load goes to the max value. So here 256 would be the max value of the load. So the load is quantized between 0 and 255. So to make this long formula short, here we try to give a higher cost when the link is delay becomes larger. But there is an issue that we need to discuss. What happens in a network when we do least delay routing? So that happens in communication network. The same occurs with Google Maps and with road traffic, where you would be tempted when you go from A to B to look on the map and see what is the one that will take the shortest time. In fact, this is what you will do if you use Google Maps or Apple Maps. So let's see what can happen. Well, the first thing, let's see on this example here. Here I have a network, and I have links that are thin. That means those links have a small capacity, but they are short, so they have a small delay. And links that are thick, but they are long, so they have a large capacity, but also a large delay. And to simplify the story, I assuming that I have a linear approximation of the delay. For example, on this link, the delay is 48 milliseconds plus B1, where B1 is the amount of traffic that flows here. On this link, the delay is 2 milliseconds plus 10 B1. So it has a smaller propagation time. It's a shorter link, but it has smaller capacity, so the delay increases more rapidly. Of course, those are values that don't make sense globally. a linear approximation is only true when you are far away from the bottleneck capacity, but let's admit those values here. It will make the example simple. And assume, like before, that I have a large amount of traffic, here 6 gigabit per second, that I need to carry through this network. And assume I use the Cisco formula that said before, that computes the delay costs that are delayed. Then what will happen eventually, like I've explained by hand waving a few minutes ago, is that the traffic will equalize on the links. And eventually, if it reaches an equilibrium, if the traffic is constant, the delays on the different paths will be equal. Because if the delay on this path is smaller than the delay on this one here, then the cost will be smaller here, and the shortest path routing will send more traffic on this, which will cause the delay to increase, and eventually it will not change when the delays are equal. So the point of equilibrium that we reach, usually in such networks, is called the wardrop equilibrium. So wardrop equilibrium is the routing decisions that results at equilibrium when every bit of traffic is trying to choose the path that has the shortest delay. So that's the equilibrium we reach in a road traffic scenario when everybody uses Google Maps, for example. So for this network, what would be the wardrop equilibrium? Oops, let's see this. We see that there are two routes, and if we sum the delay here plus here, we find that the delay is 50 plus 10 plus 1, so it's 50 plus 11b, so it's a typo here, it's 11. And it's the same in this one. So the two routes are the same, but the order of the links are changed. So the delays are equal. So if we reach an equilibrium, it will be when the volume of traffic are also equal. So here it's very easy. The wardrop equilibrium will consist in having half of the traffic going here and half of the traffic going there. If we're in a scenario where this does not occur, one of the two paths has a shorter delay, and the packets will find this path and will increase the delay. So that eventually, this is what we will have. That's the wardrop equilibrium at this situation here. Okay. Now let's assume that we change the network. We say, oh, this network is a bit congested. Let me introduce a link that will offload some of the problems. I add a new link, and this green link here is thick. So it has a coefficient 1 in front of the delay here. But it has a delay of 6, which is smaller than this one, but larger than this one here. So what happens if I add this link here and I stay from the previous equilibrium? Are we at a wardrop equilibrium for this link? Oops. Then, of course, the answer is no. If we start with the previous value, we have 0 traffic here. And we see that the delay from, if we use the green link, will be 6, plus the value here, 2 plus 10 times 2. So it will be 22 plus 6, 28, which is less than the delay there. So the green path is advantageous. So if we start from this, some packets will say, oh, I have a better path. So they will go this way. So it's not the wardrop equilibrium. Alternatively, we could compute the delay through the route that uses the green link, which is a route 154. The delay is smaller, so one of the routes has a smaller delay. It's not a wardrop equilibrium. So some traffic will be attracted by this route here. And what is the wardrop equilibrium now? Well, how do we compute that? Well, we compute the delay given the fractions of traffic. So I have an amount of traffic B2, which is the traffic that goes here, an amount of traffic B3, which is the traffic that will stay on the blue link, and B5, that is the one that will use the green link. And the traffic on this first link is B3 plus B5, and the traffic on the last link is B2 plus B5. So those are the two decisions we need to take here and there. There are 3 variables, B2, B3, and B5. I have 3 paths, so I have 3 delays that must be equal. That gives me 2 equalities. And then the total traffic should be 6. So I have 3 unknowns, 3 equations. I can solve this. And this linear approximation is very simple. We solve this and we find that it's 2 gigabits on all of the paths, which means that here 4 gigabits will go here, 2 will go there, and here we will split again equally between the two. But the delay now is 92 milliseconds on all the routes here. If we compare to what we had before, the delay was 83 milliseconds. So by enabling link 5, we make the delay worse, 92 milliseconds for everyone here. So this is an example where adding capacity in a network can make things worse, or here does make things worse here. So this is known in originally road traffic, but there's also a recent paper of Frank Kelly that analyzed the same thing in the context of the internet. If we use link costs that reflect the delay, and therefore the shortest path calculations will lead to word drop equilibrium, then such a network is subject to the Brace paradox here, which of course means that shortest delay routing is not optimal. Of course, you can say, well, this is also not a very nice network engineering decision. Here I've added a link that goes from a bottleneck to another bottleneck, so it's not a good idea. It would be better if I added a green link straight through here. That would have improved things. But the truth is that in networks, bottlenecks are moving. Here I'm showing the bottlenecks are here, but this might not be a static bottleneck. It may be a bottleneck simply because there's a huge amount of other traffic that it's competing to, and this changes. So adding arbitrary capacity in a network is not necessarily making things optimal. It can make things better. But in fact, what we have is an instance of cost of hierarchy. We have a game here where every packet is trying to find the shortest path, and the resulting equilibrium that we find here is not necessarily optimal, like we have in game theory. And the non-optimality is called the cost of hierarchy. So that is what happens in networks if we simply do shortest path routing or shortest delay routing. So if we want to do optimal routing in a network, then we need to work. We've seen that shortest path are not optimal, shortest delay also not. So there are various things that can be done. One of them that is found in papers is to implement an optimization problem and do it in a distributed way. It can be done, and some experimental networks did it, but it's not very much done today. What is done more frequently today is to have an offline optimization procedure where you measure the volume of traffic and the delay everywhere in the network. And then there are two philosophies that can be used. One is to use technologies like SDN, for example, and entirely bypass the routing protocol to compute short optimal paths. That's an option that works well in small networks. What is most often done is that you use that to tune the link costs. So instead of tuning them in a brutal way, like I showed before, by simply reflecting locally the delay, you take this as a, of course, non-linear optimization procedure, and you ask what are the link costs that would lead to an optimal utilization of all my network links. So how much traffic should I deflect to longer paths here indirectly by changing the link cost? So that can be done. Of course, this is not a real-time thing. This is typically using machine learning heuristics, and the resulting link costs are set into all routers. The benefit of this is that by having a two-time approach, we still have fast reactivity to anything that can happen in the network. If the network becomes partitioned, or if a link fails, or if a router fails, we still have the shortest path routing with the costs that were set at the last update from the central manager that will find another route here. Voila, that's the conclusion of this module. Distance vector is simple and smart. Smart because the algorithm, the distance vector, the distributed Bellman-Ford algorithm, and we've seen it's not so centralized. Centralized Bellman-Ford is easy to understand. It simply computes the it updates the cost by adding more and more hops. But we've seen it's smarter than that. It works whatever the initial condition, it always comes back on its feet. But we need also to be careful and add in the distribution way, we need to add this case that says, if I receive an update from what I knew was next hop before, I need to take it even if it's larger. So if we do this, and we have extremely compact code, also very small information, so that lends itself well to simple scenarios where we need a very low footprint and little or zero configuration. But it's relatively slow in terms of convergence, so it is typically not used as is for large and complex networks that most of the time today use link state protocols, at least inside an area. We've seen that shortest path routing is better than spanning tree protocol, but is generally not optimal, and that optimal routing requires another layer of optimization. And also that link delay as link cost is not optimal, and Brace paradox is something that we need to be aware of. Voila, that's the end of the course and of this lecture today. Here I've called Bart and Lisa to join us and wish you a Merry Christmas, and I hope this course was useful to you.